The Tilbury 2 approach bridge installation represents a major milestone in the development of the new port infrastructure for the southeast of England, overseen by Forth Ports. As part of the new Tilbury 2 terminal, a 360-ton steel bridge was lifted into place, marking the first of three components required for a roll-on roll-off RORO facility that will serve the port. This installation is key to expanding Tilbury's capabilities, enhancing its ability to handle increased volumes of freight efficiently. Once the Matador 3 was aligned, the bridge was carefully brought into place, marking the completion of the installation phase for the first component of the new terminal's RORO facility. This bridge will provide essential access for vehicles and freight to move between the terminal and ships efficiently, playing a critical role in streamlining port operations at Tilbury 2. The bridge was fabricated in Rotterdam, Netherlands, and transported 135 nautical miles to Tilbury. The journey, which took 24 hours, involved towing the massive structure by sea. Once the bridge arrived at the site, the next critical phase involved precision lifting and placement onto its supports. The operation was carried out by the Bon Mees Matador 3, a heavy lifting vessel with an impressive lifting capacity of 1,800 tons and a maximum lift height of 80 meters. The dimensions of the bridge, measuring 54 meters in length, 15 meters in width, and 5 meters in height, required careful coordination to ensure the structure was positioned correctly. The installation process commenced with the Matador 3 lifting the bridge from the H332 barge, a delicate maneuver that had to account for the river's tidal conditions. High tide on the River Thames provided the ideal conditions for the final positioning of the bridge. This successful installation highlights the scale and complexity of the Tilbury 2 project, which is designed to enhance the port's infrastructure and position it as a key logistics hub in the UK, capable of handling significant trade volumes and boosting the region's economic growth. The application of additional concrete is a crucial preparatory step in the reconstruction of the mega supports on the Elbmarsch elevated highway, K20. This process involves reinforcing existing structural elements by adding layers of high-strength concrete to enhance their load-bearing capacity. This is done to ensure that the bridge can safely handle the increased stress during the demolition and reconstruction phases. The extra concrete fortifies key areas, allowing the transfer of loads from the original mega supports to temporary structures. This reinforcement is vital for maintaining the structural integrity of the bridge while the old supports are being dismantled. Temporary support and load transfer is a critical phase where specially designed support structures are installed to bear the weight of the bridge while the mega supports are demolished. These temporary supports stabilize the bridge by redistributing the load from the existing supports to the new structures. This ensures that the bridge remains operational, preventing any disruption to traffic and port activities while the old supports are dismantled and reconstructed. The demolition of the mega support involves carefully dismantling the massive 173-ton structures once the load is transferred to temporary supports, ensuring precision to avoid any impact on the bridge's stability. The demolition of the crossbeam employs a sliding track system, allowing the safe removal of the massive 866-ton structure. The crossbeam is gradually shifted and lowered in controlled sections along the track. This method ensures precision, minimizing risks and maintaining the bridge's structural integrity during the replacement process. The construction of the new crossbeam on a support structure begins by assembling the crossbeam components on specially designed temporary supports. The new crossbeam, made from pre-stressed concrete, is built section by section to ensure stability and strength. This process ensures the crossbeam can handle increased traffic loads. Precision engineering is used to align the structure accurately, and advanced materials ensure long-term durability before it is integrated into the bridge's framework. The construction of the new mega support involves fabricating a robust structure with a diameter of 6 meters and a height of up to 7.3 meters. Using high-strength materials, the support is built to meet modern safety standards, ensuring it can accommodate increased loads from the expanded highway effectively. The removal of the temporary support occurs once the new mega supports and crossbeams are securely in place, allowing the load to transfer back to the permanent structures. Following this, final work includes sealing joints, applying protective coatings, and conducting thorough inspections to ensure structural integrity. Finishing touches, such as pavement restoration and installation of safety barriers, are completed to enhance functionality and aesthetics, ensuring the bridge is ready for safe traffic operation. Opened in 1975, the 3.84 kilometers long structure holds the distinction of being the country's longest motorway bridge. It plays a vital role in facilitating traffic to and from the Port of Hamburg, one of Europe's largest and busiest seaports. In Walpertskirchen, a crucial infrastructure project unfolded during Week 44 with the replacement of a 19th-century bridge. The old structure, which had long served the region, was demolished during a 4-day closure period. This operation marked the culmination of a significant modernization effort aimed at improving transportation efficiency and safety in the area. The installation of the new bridge was a complex and highly technical process. The newly constructed bridge, weighing approximately 1,400 tons, was carefully shifted into place using an advanced sliding system. This system, powered by hydraulic cylinders, enabled the precise movement of the massive structure. Over the course of the operation, the bridge was moved 34 meters to reach its final position, bridging the gap that had been left by the old structure. This innovative sliding system was essential in ensuring the smooth and controlled movement of the bridge, reducing the risk of damage to both the structure and the surrounding environment. Hydraulic cylinders were strategically employed to provide the necessary force and control, allowing for a seamless transition into the bridge's permanent location. The 4-day closure period was meticulously planned to minimize disruption to the local community and transportation networks. During this time, construction teams worked intensively around the clock to complete the demolition of the old bridge and the installation of the new one. By compressing the work into this short period, the project avoided prolonged closures that could have impacted residents and businesses in the area. The successful insertion of the bridge in Walpertskirchen reflects the advancements in engineering and construction techniques that make such projects feasible within relatively short time frames. The new bridge not only replaces an outdated structure, but also symbolizes the ongoing efforts to modernize infrastructure in the region, ensuring that it meets the demands of contemporary transportation needs. The innovative sliding system used in the bridge installation at Walpertskirchen was crucial to the success of the project, enabling the safe and precise movement of a 1,400-ton structure into its final position. Traditional methods of moving such massive structures can be risky and involve significant challenges, but the advanced sliding technology ensured that the bridge could be relocated with minimal disruption or risk of damage. The system relied heavily on on hydraulic cylinders, which are known for their capacity to generate immense force while maintaining fine control over movement. In this case, hydraulic cylinders were strategically placed to push and guide the bridge over a distance of 34 meters. These cylinders applied consistent pressure, ensuring the bridge moved incrementally and evenly, preventing jerky or uneven motions that could destabilize the structure or cause damage. Hydraulic sliding systems are ideal for projects like this because they allow for highly controlled movement, which is critical when dealing with heavy, delicate structures like bridges. The gradual, step-by-step movement facilitated by the hydraulic cylinders allowed for constant adjustments, ensuring that the bridge was perfectly aligned as it moved toward its final position. This level of precision is especially important when working within tight spatial constraints or where the ground underneath needs to remain stable, as was likely the case in Walpertskirchen. Additionally, the sliding system likely included a set of tracks or rails upon which the bridge moved, further enhancing the smoothness of the operation. These tracks would have minimized friction, allowing the hydraulic system to push the bridge with greater ease and efficiency. The system was designed to distribute the load evenly, preventing stress points that could have damaged the bridge or the mechanisms used to move it. Another key advantage of using such a system is its ability to protect the surrounding environment and infrastructure. The controlled movement reduces vibrations and disturbances to the surrounding ground, limiting the risk of damage to nearby buildings, roads, or utilities. In environments where stability is critical, such as near railways, as is often the case with bridge projects, this is a significant benefit. Kurosaki bypass Haru-no-machi ramp overpass construction installation of girder with a 3,000-ton class crawler crane. The Kurosaki bypass is an essential infrastructure project located in Kitakyushu City, Fukuoka Prefecture, Japan. This bypass spans a total length of 5.8 kilometers, providing a dedicated roadway with 2 lanes on each side. It serves as a key transportation artery that connects Nishi-Hanmachi 1 Chome in Yahata Higashi Ward to Jinoharu in Yahatanishi Ward. As part of this bypass construction, one of the most critical components is the Haru-no-machi ramp overpass, which passes over a railway line, the junior overpass section. Given the structural demands of this project, a specialized approach was necessary for the installation of the bridge girder. In this specific phase of the construction, a 3,000-ton class crawler crane was employed to install the upper structure, girder, of the overpass in a single operation. The use of such a massive crane highlights the complexity and scale of the project, demonstrating the need for advanced engineering techniques and heavy-duty equipment to ensure both efficiency and safety during the installation process. Overview of the Kurosaki bypass. The Kurosaki bypass is a vital part of Kitakyushu's urban development and transportation network. By alleviating traffic congestion on local roads and providing a faster route for vehicles traveling between the Yahata Higashi and Yahatanishi areas, the bypass enhances the city's infrastructure. This 5.8-kilometer roadway is designed as an expressway with limited access, meaning it is dedicated to automobile traffic only, further enhancing its utility for reducing traffic jams and improving the flow of goods and people across the city. One of the most challenging aspects of the Kurosaki bypass project is the construction of the Haru-no-machi ramp, which crosses over the junior railway lines. Such projects demand meticulous planning and the use of specialized equipment, particularly when installing the upper structure of an overpass. Before the installation of the girder, the assembly of the bridge components took place at ground level. This process is known as ground assembly, where all the individual parts of the bridge, including the girders, are carefully put together on the ground before being lifted into place. Ground assembly offers several advantages. First, it allows for precise construction and inspection of each component before installation, reducing the potential for errors or misalignment when the pieces are placed atop the supports. Second, it enhances worker safety by reducing the amount of time spent working at height. For the Haru-no-machi ramp, the girders were constructed on the ground and then lifted in one piece to be placed on the bridge supports. The use of pre-assembled girders can significantly streamline the construction process, saving time and ensuring that the bridge sections are properly aligned and secure. The materials used in constructing the girder were of high-grade steel to ensure the durability and strength necessary for an overpass carrying heavy vehicle loads. Specifically, the construction utilized 90 steel plates, each measuring 25 millimeters in thickness, 6 meters in length, and 1.5 meters in width. 68 steel plates, each measuring 40 millimeters in thickness, 6 meters in length, and 2 meters in width. These steel plates were assembled to form the girder, which serves as the backbone of the bridge's upper structure. The use of such thick and heavy steel ensures that the bridge can withstand both the static loads from its own weight and the dynamic loads from vehicles passing over it, as well as environmental factors like wind and seismic activity. One of the most impressive aspects of this construction project is the use of a 3,000-ton class crawler crane for the girder installation. This crane, a behemoth in the world of construction machinery, was critical to lifting the pre-assembled girder into place in a single operation. The crane's specifications are equally impressive. Its main boom can extend up to 262 meters, although in this particular project, it was utilized at approximately 100 meters in length. Crawler cranes are typically used for heavy lifting tasks due to their high stability and load-bearing capacity. They are mounted on tracks, or crawlers, which allows them to move easily over rough or uneven terrain, a crucial feature in large-scale construction projects like this one. The crane's massive lifting capacity allowed the construction team to move the assembled girder in one lift, minimizing the risk of misalignment or structural stress that can occur if the girder were installed in multiple smaller pieces. The Kurosaki Bypass Haru-no-machi ramp overpass construction represents a monumental engineering achievement, combining meticulous planning, advanced construction techniques, and the use of heavy-duty equipment to complete the project safely and efficiently. By utilizing a 3,000-ton class crawler crane to install the girder in one go, the construction team ensured that the overpass was installed with precision and in a time-efficient manner. This project, part of the larger Kurosaki bypass, plays a key role in improving transportation infrastructure in Kitakyushu City, supporting economic growth and providing a safer, faster route for vehicles traveling across the city. The successful installation of the girder using ground assembly techniques and the crawler crane serves as a testament to modern construction capabilities, ensuring the longevity and reliability of this vital transportation link. The construction of the world's longest bridge over water, currently underway in the Pearl River Delta, marks a monumental engineering achievement. This 50-kilometer-long bridge is designed to connect Hong Kong, Macau, and Zhuhai, forming a key part of a larger infrastructure project that aims to integrate the cities of the Pearl River Delta region. The Hong Kong Link Road is a critical component of the Hong Kong-Zhuhai-Macau Bridge project, serving as a vital connection between Hong Kong International Airport and the boundary of the Hong Kong Special Administrative Region, HKSAR. This 9.4-kilometer-long viaduct is designed to accommodate high traffic volumes with a dual 3-lane carriageway, ensuring efficient movement of vehicles between Hong Kong and the main bridge. The viaduct aqueduct stretches across the waters of the Pearl River Delta, requiring advanced engineering techniques to address the challenges of building in a marine environment. The elevated structure allows uninterrupted navigation for ships, while also providing a stable and durable route for vehicular traffic. The dual three-lane configuration is essential for handling the expected heavy traffic flow, especially given the strategic importance of the bridge in connecting major economic hubs. In addition to serving as a transportation link, the Hong Kong Link Road is part of a broader infrastructure plan to improve regional connectivity and reduce travel times between Hong Kong, Zhuhai, and Macau. The installation of 12,600 tons of steel reinforcement cages is a crucial part of the Hong Kong-Zhuhai-Macau Bridge's structural integrity. These steel cages, used in the foundation piles, reinforce the bridge's concrete structures, ensuring they can withstand immense loads and environmental stresses, such as strong currents and high winds. Precision in installing these cages is vital, as they provide the core support for the bridge's massive superstructure, distributing weight and enhancing stability. In addition to steel reinforcement, the placement of 63,900 cubic meters of concrete further strengthens the bridge's foundation. The concrete is poured into deep foundation piles, binding with the steel reinforcement cages to create a solid, durable base that resists both the forces of the ocean and the weight of the bridge. The combination of steel and concrete ensures the longevity of the structure, allowing it to support high traffic loads and withstand the demanding marine environment.